we have some understanding of the gradient, we want to go to this problem. Now, this is from Khan Academy, and I can't do half or a quarter as well a job of explaining this as they do in these videos, so I definitely recommend that you take a look at these videos, but I'll just make some comments here. So here we have a task which is to maximize a function. And this function is clearly a function of two variables, and we can see the way it's constructed here. So it's x squared y. So we want to maximize it or minimize it depending on the task. Here they want to maximize it. And of course, in first semester calculus, we talk about the idea of maximizing or minimizing a function, and we also talked about it in the previous discussions when we said we wanted to find the minimum of the error function. But anyway, in first semester calculus, we do talk about this kind of problem. So, you know, we might have some kind of curve like this blue one, and we want to find the lowest point or the minimum. And we learn in that first semester calculus that we can use the derivative because the derivative tells us the slope, and usually the slope will be 0 at the minimum, also at the maximum. So we can use that fact, so we can set the derivative equal to 0 and find all the points where the slope is 0, and that will certainly help us to find the minimum. Instead of having to look at every possible point, we only have a very small set of points here. There's just one point where the slope would be 0. So we can do something similar when we have two variables, and you don't cover that in the first semester of a calculus course, but you might cover it in like the third semester. And it does involve taking derivatives, but it involves in particular taking partial derivatives, because taking the regular derivative here sort of doesn't make sense. You have to talk about partial derivatives. But we can do something like that. And in fact, in the textbook that I've been following, they do cover how to do that. But here, if we look at this function and we ask what's the maximum, you know, and if this might be the picture of this function, well, it looks like it goes up forever. So there is no maximum. Basically in the same way that in this function also there's no maximum. There's a minimum, but there's no maximum. Now I think of that other function, there's not even a minimum, but still in this function here, there's also no maximum. However, if we said, oh, well, we're only going to look between here and here, then we can talk about the maximum. Maybe the maximum is up here, or maybe it's over here. I'm not really sure. But, you know, we can talk about the maximum in that case. We say we're going to look at every point between here and here, then there is a maximum. And we're going to have the same kind of situation in that other picture. So we're not going to, so we admit there's no maximum in an unconstrained way. If there's no further constraints, we just say, where's the maximum of this function? There's no maximum. But if we restrict ourselves to a certain domain, now here, we wouldn't restrict, in this picture, we wouldn't restrict ourselves just by just the x variable, or not typically, but we want to put a restriction on both the x and the y. So you know what that looks like. You know, this is the z-axis, and this is the x-axis, and maybe the y-axis is coming out. And so we're going to restrict the domain of the function to a certain set of values, and then maybe there will be a maximum for this function. Probably there is one. So here, the so-called constraint is a little bit different than you might expect, because you might expect that the constraint is sort of a circle in the xy plane, but everything inside the circle as well. But here, that's not what they're saying. Here they're saying the constraint is just the circle. Okay, so all the points on some circle in the xy plane, and this is the unit circle, I think you can recognize, but whatever the constraint is, anyway, it's just going to be like a kind of a linear constraint. It's not all the points in the xy, in the unit circle. It's just a point, or what should I say? What's the right language? Maybe that's called the unit disk. So it's not all the points in the unit disk. It's just the edge points. In other words, just the circle itself. So that's what this says. If we said less than or equal to, that would be all the points inside the circle as well. But that's not the problem. That's not what they're asking us to do. They're not saying find the maximum for all points inside this circle and this circle in the xy plane. They're saying just on the xy plane. So it's kind of a stronger restraint because we're limiting ourselves more. Anyway, whatever it is, that's the kind of problem we're trying to do here. So it's pretty similar to this. We're limiting ourselves. So like limiting ourselves to just this region, or actually what we could do is just limit ourselves just to this point and this point. That's kind of what's the analogous limitation when we say just the circle. But whatever the limitation is, there's some limitation on the input space. In this case, the input space is just x, but in the picture, the input space would be x and y because those are the inputs. So in this picture, he kind of tries to draw the the shape that this limitation imposes on this curve, this blue surface. So it's not a curve, it's a surface. So in other words, as I said, we have a circular limitation on the input space, on the xy, and then that means, at one of the points on the circle, the height is here, and another point on the circle, the height is up here, and another point on the circle, the height is in here. So we have this kind of object that we're trying to find the maximum height of, and then he sort of turns it around and he sort of rotates this whole picture so that we can look down on it and we get this picture. So we have the unit circle, and then we have the contour lines, all these contour lines which are the heights. So every point on a contour line, as we've discussed, every point on a contour line has the same height above it for the surface. So that's what these are. These are kind of equivalue lines here, because they say that every point on here has the same height or the same value. So actually there's some more here. There's one drawn here and one drawn here and so on. And of course, as we move out in this direction, the surface that we were talking about gets higher and higher because that's what this picture looks like. As we move out, things get higher and higher, at least in this direction. I guess it doesn't happen in this direction and also in this direction. I guess if we move in this direction, it gets lower and lower. But anyway, in some directions, it gets higher and higher. And so as we move out, we're getting higher and higher, which we want to do. We want to get higher and higher. But there's not going to be any maximum if we don't have any constraints. But we do have some constraints, and so there probably will be a maximum. So we want to move out, 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 but we can't move past the red constraint. That's where in fact, we can't even move. We're not even allowed to be in here because we have to be on the circle. That's because it says equals, not less than or equal to. So, but anyway, we can see that at different points on the circle, we're going to have different heights. So we need to find the highest point when the xy coordinates are on the circle. So in the video, he says, well, what about like if we think about f of xy equals 2, that is, this equals 2. So that means that there's we're talking about cutting the surface at height 2. So we imagine taking a plane that's parallel to the xy plane and has a height of 2, and just looking at where it cuts the surface. And that will be, if we look down on that, we'll see all the xy points that have a height of 2. So maybe this is the set of points that where the height is 2, and this. So maybe we can do better than 2. So if we look at like f of xy equals 3, maybe it'll look kind of like this. So it will cut the circle. It'll still cut the circle. It'll still touch the circle. So that means somewhere on the circle, f of xy is equal to 3. And so we want to, as we said, we want to sort of move out. So here he moves a little bit further out, and here he's moved too far out. So we might get like a high values for the height of the surface, but we're not satisfying the constraint. So we've moved too far away or too far out. So this is the perfect place to be, because if we go any further out, we're not going to be on the constraint. We're going to not be obeying the constraint. but we've moved as far out as we can. In other words, we've made the function as high as possible, and so we see that right here would probably be like the best point, or maybe right here would also work just as well. So that's the idea visually, but the question is, how do we find this? How do we find this point? So that's not easy. But the solution, I guess, came from this French mathematician. Apparently, he was born in Italy, but his was French. So anyway, his name was Lagrange, and he somehow understood one further detail about this picture. Now, it's not exactly 100% clear to me that his observation is right, but that's due to my own limitations, I guess. But anyway, what he said is that when you reach the place where they just touch, their tangent lines are going to be the same. In other words, the slope of what is color is this? The blue curve and the slope of the red curve, when they just touch, the slope or the tangent line will be exactly the same. So that's his insight into this problem, which it certainly looks possible, but I'm not 100% sure that it's true, but maybe there's some other way to show that it is true. But that's the insight anyway that will allow us to find which point it is. Let's go on to the next video, and maybe we'll have a nice picture of that. So here's this picture again in the next video, and here he kind of blows it up a little bit, and he's trying to show in this zoomed in version that it looks plausible that the slopes are the same right where they touch. Now, just a few minutes ago, we made the argument that the normal vector to any tangent to any line will be perpendicular to the line. And that's sort of what this is showing. Because if you take this curve, for example, you can think, oh, there are many different tangent lines on this curve. So you can imagine there's a tangent line right here, another tangent line here, and another tangent line here. And we know that for any of those tangent lines, we can draw a normal vector, and that will be perpendicular. And we know how to get that normal given a particular tangent line. We just take the A and the B as we described it before, and take those coordinates, and those will be the vector that is normal. So in this picture, also, I can take the normal right here for this tangent, and I can look at another tangent, normal, and I can look at another tangent and normal. And right here, I can look at a tangent, and the normal will be pointing in this way. And then for this blue line, I can do the same thing. I can take, here's a tangent, normal, or maybe normal would go this way, but it doesn't really matter. It's just perpendicular is what we want. And another tangent line here, normal in this direction or in this direction. And right here, same thing. So we can rephrase Lagrange's insight. Instead of saying that the tangent lines are the same at this point, we can say that the normal lines are the same, or at least they're in the same direction. Maybe one points this way and one points this way, but they're parallel to each other, or they're multiples of one another. So that's kind of a nicer, sort of a nicer way to rephrase what Lagrange said, or what he saw, which is that the tangent lines are the same, or the slopes are the same, or the normals are the same, or actually more carefully, that they are multiples. One is a multiple of the other one. Okay, so there's one more thing we want to say, which we've also already covered, and that is we talked about the gradient already. And we said that the gradient tells us the direction of greatest increase. So suppose we're right here, right on this here. Now, if I walk in this direction, I'm not changing the height at all, right? That's what this contour line means. I mean, at every point one here has the same height. The surface is the same height at every point on this curve. So if I'm right, where did I say? If I'm right here and I walk in this direction, I'm not changing the height at all. So that is definitely not the direction of the gradient, because the gradient will give us the most increase, and this gives us 0 increase. And the same way here, if I walk in this direction, that's not going to give me any increase either. So that is definitely not the direction of the gradient, because as I said, the gradient gives us the direction of greatest increase. So what is the direction of the gradient, say right anywhere, right here, right anywhere? So it's pretty clear that the gradient is the normal. Is the normal to the curve at that particular point. By the normal, I mean you take the tangent line at that point, and then we can talk about the normal to that tangent line, the vector which is perpendicular to that tangent line. So that's what I mean by the normal. And it's pretty clear that the direction of greatest ascent or increase is in that direction. So that's one more maybe observation. I'm not sure if that comes from Lagrange or not, but maybe it does. Or anyway, it's a very good observation. So the gradient is the direction of greatest ascent, and that will be the normal vector to the curve at the particular point. And remember, that sounds a little bit strange, but what we mean by the normal is we draw the tangent line there, and then we can talk about the normal of that tangent line, and that's what we mean by the normal at this particular point on the curve. So now we just want to write all of this down. So first, over here, this is the direction of the gradient for the blue one. And maybe the direction of the gradient for the red one is maybe just the opposite, but as we said, it's going to be a multiple of the blue one. Maybe it's the negative multiple, and it doesn't have to be the same length, but it's going to be in this direction, one of these two directions. So we said that the slopes are equal, or the tangent lines are the same, and then we turned that into that the normal vectors point in the same direction or multiples of each other, and then we turned that and we said that the gradient is in the direction of the normal, so the gradients are multiples of each other. So the gradient for the one curve and the gradient for the other curve are multiples of each other. That's what we want to write down. Let's see where he writes that. First of all, he draws another gradient for the red one. He has it pointing in the same direction. And finally, he writes the equation that we wanted to say. The gradient of the blue one is just a multiple of the gradient of the red one. And this is the expression for Lagrange multipliers. And this will give us the extra piece of information we need to find the maximum value on the curve. Remember what the picture looked like. We had this picture, but we said, and so we say, oh, the maximum's right here, but how do we know? What are the coordinates of this point? So, it looks nice as a picture, but that we're not satisfied with the picture. We want to know the actual coordinates, and that you can't get from the picture, right? You don't know exactly what the coordinates are. But now with this extra observation, it will give us enough information to find the coordinates of the point. So this is this is what leads us to the solution to our original question. Okay, so that's kind of it. But now we want to sort of work it all out. Use all these observations to actually do it, to maybe do a particular problem. So now remember that the gradient is actually a vector. So here you can see that it was a vector. Now, in our case, it's just a vector with two components. In general, it could have more components if we had more input variables, but in our example, in the picture that we were working with, we only had two components. So when we write this equation here, this is a vector equation because this is a vector of two components, and this is a vector of two components. Now, we haven't usually written vectors like as vertical. We usually wrote them as like this, as horizontal pairs, but there's no reason why we couldn't write it like that. So instead of writing them next to each other, we could write them like this, one on top of the other. So that's the way he's going to write it. But the point is that this is a vector and this is a vector. This is a scalar, but this is a vector and this is a vector. So remember, way back when we talked about what we mean when two vectors are equal, we mean that they have to be equal component by component. For example, if I said this vector was equal to this vector, I mean they're equal component by component. Now I should write this one vertically because it's just easier to see what I'm talking about. So I'm sorry for this big mess, but I'm just saying that this vector is equal to this means that these two are equal and these two are equal. That's what he's going to do. So he writes it out, the gradient of g. What does that mean? That means the partial of this g, remember g was this. Actually, we didn't say that. Well, I think we said it somewhere, or we didn't say it, but it was kind of understood that it was the circle. So this is g, and we want the partial derivative of g with respect to x and the partial derivative of g with respect to y. Now, there's one last thing. I don't think he said it, or maybe we skipped it, but g is not quite equal to x squared plus y squared. It's actually equal to x squared plus y squared minus 1. That's how he defines g. So he moves this over to the other side. But that doesn't, well, so then if we take the derivative, the partial derivative of that, I don't have the equal sign here. I make this minus 1 equals 0. And if I take the partial derivative of this with respect to x, I just get 2x. And with respect to y, I get 2y. So that's what he has here. And then we're going to put a lambda in front of it. And then we have to do the partial derivative of f, which you can't really read it here, but it's x squared plus y squared. I'm sorry, x squared times y, and that's f. And we want the same thing, the gradient of that, which means the partial with respect to x and the partial with respect to y. And we end up with this. And this is kind of the gradient representation, or the vector representation of that gradient, that observations about the gradients being multiples of each other. But once again, when these are equal to each other, it means that this has to equal this times lambda, and this has to equal this times lambda. So that's two equations, which look like this. Now that's nice, but the problem is we have two equations, but we have really three unknowns here, x, y, and lambda. So that's why we don't actually have enough information written down here yet to make this solvable. But don't forget that we have one more equation, which is that. This is also part of the system. So now we have three equations and three unknowns. Probably we can solve this and find x and y, which is what we wanted to do. We wanted to find where on the circle it's going to be a maximum. The height of the surface is going to be a maximum. And that is the idea behind Lagrange multipliers. So we get this system and we just have to solve it, and hopefully we can. So we can see that maybe we can solve actual problems like this one. We can find the actual x and the y. But what I want to stress right now is that we had an equation subject to a constraint, and somehow we managed to put all of that into sort of one bigger equation and try and maximize that whole equation. So that was a little bit puzzling to me when I first saw it. Like, how can we take an equation and sometimes this is less than or equal to, so that kind of constraint, and make it into a single equation. Now, we didn't do less than or equal to. That turns out to be trickier to do, but we talked about this. Okay, so maybe we can do a problem, or maybe we can actually do this problem, and he actually does this problem. You can watch it and see the actual solution. Okay, just for completeness, let's see how this textbook approaches this subject of Lagrange multipliers. So they start out by introducing the need for this mathematics. They say, frequently when working with applications of calculus, you will find that you do not need simply to maximize or minimize a function, but you must do so subject to one or more additional constraints that depend on the specifics of the situation. So we just talked about the constraint. The constraint was to keep the inputs within the, well, actually on the circle. So this is another example or another expression of that. Okay, so they're going to give us an example, and they're going to say that they want to minimize something, and they want to minimize the material used to make this box, but there's also going to be a constraint. So the constraint is an open rectangular box, so I guess this part here is open, having a fixed volume of 4 cubic feet. So the box has to hold 4 cubic feet of material, but we want to minimize the amount of material used to make the box. So we can say that we have a function that we want to either minimize or maximize, in this case minimize, and we have a constraint. So what we want to minimize is the area of the box. In other words, this side has an area and this side has an area, so the total area. So they call it A, and it's a function of x, y, and z. And this is the area of the box. Remember, the top is not there. So we have 1, 2, 3, 4 sides and a bottom. And this is the calculation for the area of that box, the material. And just like we did, they note that this has neither a minimum nor a maximum. I guess it doesn't have a minimum if you allow negative values. I'm not sure why they say it doesn't have a minimum, because it seems to have a minimum of 0. But maybe that's a constraint. Anyway, they say, however, we have not made use of the fact that the volume is to be maintained at a constant, and that's a constraint. And the volume, which is x, y, z, has to equal 4. So this is similar to our constraint in that, in as much as it's an equal sign. It's not a less than or equal sign. And they point out that the constraint is essential if we're going to solve the problem. If we don't have this constraint, there is no solution to the problem, because, as they said, there's no minimum. Although, as I said, it seems like there's a minimum of 0, but maybe they're talking about negative values as well. But they say, since we have a constraint, we can take this constraint and we can write it like this. And then we can take our area function, which was like this, and we can replace z by this. So what we'll have is a new area function that is given only in terms of x and y, which, when you do all the work, you end up with this. Now, we didn't cover the technique for finding the minimum of this function, but they say that they can do it. So we didn't go through it, but what they're doing is they're taking the partial of the area function with respect to x and the partial of the area function with respect to y, and setting them both equal to 0. So that's kind of like what we do in one variable calculus. We take the derivative and set it equal to 0. So they're doing something like that, but we haven't gone through the details of what you would do when you're working with partial derivatives, but we'll just accept that what they're doing is correct. And then they solve this system of equations. They have two equations here, and so they can solve for x and y. And when they go through the algebra, they get that x equals 0 or x equals 2, but they reject that x equals 0 because they're not thinking about a box that has 0 length. So the point is x equals 2, and then they solve for y, I guess, and they get 2 comma 1. And then they can figure out what the z is based on that, because we have the constraint about the volume. So I guess it's 2, 1, 2. And then it's not clear, I guess, yet whether it's a local minimum or a local maximum. And there's a little more that they have to do, and we won't go through it. but it turns out that it's a minimum. And so the solution is to make the box with a square base. So I guess that's the 2, and the 2 means the base is square, and then the height is 1. So they found the solution. So they didn't use the gradient, and they didn't use the observation that we talked about earlier about the fact that the gradient for the constraint is a multiple of the gradient of the what we call the objective function, in this case the area function. But a little bit further on, they're going to say that we need to do it that way sometimes because sometimes we can't do it the way they just showed us. So next they just say that the general description of this problem is that we have a function which we're trying to maximize or minimize. So here's a function, and then subject to the constraint, and notice that the constraint is given as with an equal sign. So we are still limited to, this method is limited to only where the constraints involve an equal sign, not a less than or equal sign. Now, just to clarify what we've said earlier, this function is, this general function is given in terms of x1, x2, x2. So the input looks like that, and we can write that as a vector, and that's what they do here. So we have g of x equals c. It's supposed to mean the same thing as this. And we have f of x is the function that we're trying to either find the minimum or the maximum of. And they kind of review what they did by saying they used the constraint, this constraint, to solve for one of the variables in terms of the others, and then substitute this variable in the expression for this, and creating a new function with one fewer variable. And then using the techniques that they used, which I guess are covered in section 4.2, we can find the maximum or minimum of this function. So she says, in theory, this is an entirely appropriate way to approach such problems, but in practice, there is one major drawback. It may be impossible to solve explicitly for any one of the variables in terms of the others. So remember here, we're going to solve for one of the variables in terms of the other. In other words, here, we're going to solve this for one of the variables in terms of the other. That's what we did up above, and that's what we're talking about doing more generally. But she says it's not always possible. She says, suppose this was your constraint. So this is not so simple anymore. So it has an exponential here, it has a cosine here, and so on. And she says there is no means of isolating any of x, y, or z on one side of the constraint equation. And so it's impossible for us to proceed any further along the lines that we just did, example 1. Okay, so now she's going to introduce the concept that we discussed, called the Lagrange multiplier. And she says it's based on this theorem, which is what we discovered when we looked at the curves, and that is that the gradient of f will be a multiple of the gradient of g at the point which is the solution to the problem. So let's read what this theorem says, although we're more or less familiar with it already. So remember in the Khan Academy pictures, it was a two-dimensional input space. So x, the point in the input, which represents the inputs, was in R2, but we want to be more general and allow for solving the problem when we have more than just two inputs. And here it says let x be in Rn. And it says let x be open in Rn. So this x refers to the set of all possible x's, and we want it to be an open set. So if you recall open sets, so we can take the set of all values between 2 and 3. The question is, do we include the endpoints or not when we're talking about that set? So if we are not including the endpoints, So any points between 2 and 3, but not 2 and 3 themselves. Uh, in that case, that's called an open set. But if we do include the endpoints as well, that's called a closed set. And you can do something similar when you're talking about not just R1 here, but R2 and so on. But we won't worry about that now. Just say we'll just be more casual about this, and we're just saying that X, the points that we're considering are in Rn, or the vectors we're considering, if we prefer to say it that way. But let's say the points we're considering are in Rn. So it means there are n elements in each for each input. And then this says that both our functions f and g have as their output just a number. And that was true in the last example. If you think about that, well, this was not the last example, but say this example. So the output, once we put in numbers into here, we'll just get a number out. So that means the output is a number. That means the output that's what this means. It means the output is a number as opposed to like a vector or something like that. And the same thing for the g function, even though it's a kind of complicated one. Still, the output, when you put in x's and y's and z's, you get out a number like this. Here we get 2. So, so both f and g output numbers. And this just means that they are continuous functions. We only want to work with continuous functions, but let's not worry about that either. And what this means is that we have our constraint, like in the Khan Academy, this constraint was this. So this was our g function, and we constrained it to be equal to 1. So this is what this says. It says we have a g function. It takes the vector, in this case the vector is x comma y. There's only 2 elements in it, but we want to be more general and allow for more than just 2 elements. So the g of x gives us some constant. So this is just the set of x's that fall on the circle, or that satisfy the constraint. And she calls that a level set of g. But you can think about that and understand that, but we won't worry about that either. Then she says that if our function f, and she says f bar s here, so that means we're only thinking about the points on the circle and thinking about the function only at those points, the f function, the function that we want to maximize. And then she says a little bit more here, but we won't just ignore that, and just says if it has an extremum, then there must be some scalar that this is true. Well, this is what we said. We said that if there's a place where the minimum or maximum occurs, then we said this, that the gradient of f will be a scalar multiple of the gradient of g at that important point. In other words, that important point is where it's a minimum or maximum, where the f function is a minimum or a maximum subject to the constraint. So at that point, this will happen. Well, we saw that visually, and she's stating it here, and I'm not sure that she even proves it, at least not right now. So she doesn't even prove it. At least we gave some sort of visual understanding of it. So she says, once we have this theorem, then what can we do? So we form this vector equation, and then this gives us a system where we have the vector equation, and then we also have our constraint. Well, we did that also. We said we had this, and then we also had this. We put that as well in our list of equations. And then remember, we got 2 equations from this because x was in R2, so we had an equation for x and an equation for y. Well, here, since we're being more general, we're not going to just have 2 equations. We're going to have n equations because that we're talking about having n inputs. So we're going to have a vector with n equals lambda times another vector with n. And so we're going to get equations like where this equals this times lambda, and this equals this times lambda, and so on. So we're going to get many equations. In fact, we're going to get n equations, and that's what she writes here. We get the n equations, and each one of them can have all of the variables in it, here and here. So we get these n equations, and then we have our constraint, just like here. We have the constraint as well as one last equation. And then she says that this scalar is called the Lagrange multiplier. And it's named after this person that discovered this in this time. So that's this lambda here, all of these lambdas, and it's this lambda here. So that's called the Lagrange multiplier. So she says, let's go back and try this on the previous problem that we just solved in example 1. So we had this function, and we were trying to minimize it. And we had this constraint as well. So now we have to take the gradient of f and the gradient of g. But that means taking the partial derivatives, writing them vertically instead of writing them horizontally. We don't have to do that, but it looks better if we do it. It's sort of easier to understand if we do it that way. So we take the partial, remember that the gradient is a vector of partial derivatives. So we have to take the partial derivative with respect to the first variable, and the next one is the partial derivative with respect to the second variables, and so on. So that's what taking the gradient means. And so we have to do that. And we're going to get, this one equals lambda times this, the gradient of the first one here, and then this one equals lambda times the gradient of the second one, right, and so on. So that's what we get here, but here, in this case, we have only 3 variables, or we have 3 variables, so we're going to get 3 equations. So what's the first one? Let's try. The partial with respect to x of this is 2y, 0, and z. So 2y and z, and the partial of v with respect to x, where's v, here's v, is yz. So we get yz and then lambda. We can't forget the lambda. So we get that, this equals that, this equals that, this equals that, and we get this one. So she says we don't really care what lambda is. It's just a tool. This method is to help us to find what x, y, and z are, not what lambda is. Lambda is sort of introduced into the problem to help us solve for what x, y, and z are. So she says, let's do the following. Let's solve this thing for lambda, solve this thing for lambda, solve this thing for lambda, and then write what we get all equal to each other. So we get, I guess when we do that, we get this. Now this is a little peculiar to do math on this kind of thing, right? Usually we do math just on something with one equality. So it's a little not normal to do math with things that have 2 equality signs. So you have to sort of think about what you're doing, I guess. But let's just say that this works out, that we can go from here to here. Okay, so now we get this. And so we really have 2 equations. This one, and then another one, this one. We have 2 equations. And so she says the first equation gives us this, I guess, which means this. So we get this for the first equation, and the second one gives us this. So now we have x in terms of y and z in terms of y. We can go back to here and have everything in terms of y, and then we can solve for y. And she says that the work agrees with the way they did it in example 1, where they didn't make use of the concept of Lagrange multipliers. They just did it sort of by hand, so to speak. So this is our answer. And remember what the question was. We wanted to find the minimum of this, but given a certain constraint, and I call it a linear constraint. It's a linear constraint in the input space. So what I mean by linear is that we are not asking for the contents, the disk,